Next we'll work example 14.12, calculating the vapor pressure of a solution containing an ionic solute. So we saw earlier that we calculate the vapor pressure by multiplying the mole fraction of the solvent times the vapor pressure of the pure solvent. And we saw that if we have a non-volatile solute, that we simply need to calculate the mole fraction of the solvent and then multiply times the vapor pressure of the solvent. We don't have to calculate the solute in with the vapor pressure, so we don't have to add the total pressures together because the solute isn't volatile. But in this case, we have a further complication because calcium nitrate ionizes, and so having an ionic solute means that we have to consider the total number of particles as the solute because this is a colligative property. So let's read the problem. A solution contains 0.102 moles of calcium nitrate and 0.927 moles of water. Calculate the vapor pressure of the solution at 55 degrees C. The vapor pressure of pure water at 55 degrees C is 118.1 torr. Assume that the solute completely dissociates. So in order to work this problem, we just need to calculate the mole fraction of the water and multiply that times the vapor pressure of pure water, but the mole fraction of the water is going to be lessened by the fact that the calcium nitrate dissociates. So let's see how we work this problem. So what we need to do to calculate the mole fraction of the water is put the moles of water on top and multiply the moles of calcium nitrate that we put in times 3 to account for the dissociation, because calcium nitrate dissociates into calcium 2 plus 2 nitrate ions. So we have a 1 to 3 ratio for the dissociation. So for every 1 mole of calcium nitrate that we put in, we get 3 moles of ions out. And this is a colligative property, so it doesn't matter what type of ions they are, but we get the same effect from the total number of ions. So we put the moles of water on top, 3 times the moles of calcium nitrate on the bottom, and then add that to the moles of water on the bottom to give us the total moles. So we get 0.927 moles of water, and then on the bottom 3 times the moles of calcium nitrate that we put in plus the moles of water for the total, giving us 0.7518 for the mole fraction of water. Now the vapor pressure of the solution then is the mole fraction of the water times the vapor pressure of pure water at that temperature. So that's 0.7518 times 118.1 torr, giving us 88.8 torr. Next we'll work for practice 14.12. A solution contains 0.115 moles of water and an unknown number of moles of sodium chloride. The vapor pressure of the solution at 30 degrees C is 25.7 torr, and the vapor pressure of pure water at this temperature is 31.8 torr. Calculate the moles of sodium chloride in the solution, assuming the solute completely dissociates. So we need to know that sodium chloride dissociates into sodium and chloride ions. So for every 1 mole of sodium chloride we put in, we get 2 moles of chloride ions. So we'll need to multiply 2 times the sodium chloride to get the amount of sodium chloride that we put in. We also need to know that the vapor pressure of the solution is equal to the mole fraction of the water times the vapor pressure of the pure water. So the mole fraction will be affected by the amount of sodium chloride and the ionization of the sodium chloride. We can rearrange this equation to say that the mole fraction for the water is equal to the vapor pressure of the solution, which is due to the water, divided by the vapor pressure of the pure water. And that's going to be equal to 25.7 torr divided by 31.8 torr. So that's equal to 0.808176. So from the vapor pressure of the solution and the vapor pressure of the pure water, we were able to get the mole fraction of the water. We also know that the mole fraction of the water is equal to the number of moles of water divided by the moles of water plus the moles of sodium chloride, or the moles of ions due to the sodium chloride. So that's going to be equal to 2 times the number of moles of sodium chloride. So that's going to be equal to 0.115 moles for the water divided by 0.115 moles for the water again, plus 2 times the number of moles of sodium chloride to give us the total moles in the denominator. So now we can say that 0.808176, which is the mole fraction for the water, is equal to 0.115 moles divided by 0.115 moles plus 2 times the number of moles of sodium chloride. Okay, so now we can solve for the moles of sodium chloride. So we saw earlier that 0.808176 is equal to 0.115 divided by 0.115 plus 2 NaCl. Alright, and so what I'm going to do is multiply both sides by the denominator. So 0.115 plus 2 NaCl times 0.808176 is equal to 0.115. Okay, so I'm going to distribute now, and I get 0.09294024 plus 1.616352 times NaCl equals 0.115. So now I'll bring this number to the right, and I get 1.616352 times NaCl equals 0.115 minus 0.0929424. So I'm going to divide by this, and I get NaCl is equal to, and I'll just write the answer down, 0.01365. So the original moles of sodium chloride added were 0.0137 moles.